2.6 is about the combinations of functions in composite functions. So the first thing we need to talk about is the domain of a function. So if a function f does not model data or verbal conditions, its domain is the largest set of real numbers, for which the value of f of x is a real number. You want to exclude from a function's domain real numbers that cause division by 0 and real numbers that result in an even root, such as a square root of a negative number. So let's go ahead and find the domain of each function. So f of x equals x squared minus 7x. So because there is no division nor square root, that means that the domain is the set of all real numbers. So the domain of f is equal to negative infinity to infinity. Now let's go ahead and look at g of x. So because division by 0 is undefined, we have to exclude the values in the domain that cause the denominator to be 0. So we need to look at the x squared minus 2x minus 3 and see when this becomes 0. So let's set it equal to 0 and then solve. So let's try and factor the left-hand side. Well, this factors as x minus 3 times x plus 1. And so setting each piece equal to 0, you get x minus 3 equals 0 and x plus 1 equals 0. So we get x equals 3 and x equals negative 1. So those are the two values of x that we are not allowed to have. So the domain of g is from negative infinity to negative 1, union negative 1 to 3, union 3 to infinity. So what this means is we're going right up to those points, but we're not including those points in the domain. Now let's look at part C. We don't want to have the underneath become a negative number. So for positive even roots, we can only have 0 or greater. So what you're going to want to do is you're going to take the 3x plus 12 and set it greater than or equal to 0. And then solve. So we get 3x is greater than negative 12. And so x is greater than or equal to negative 4. So the domain of h is negative 4 to infinity. And go ahead and pause the video and try the last one for yourself. So in this one, it contains both an even root and a division. So we know that if it was just an even root, it's greater than or equal to 0. But because we can't divide by 0, it has to be strictly greater than 0. So we're going to take the 14 minus 2x, and we are going to set it greater than 0. So we have a negative 2x is greater than negative 14. And so x is now less than 7 because we divided by a negative number. So the domain of J is negative infinity up to 7. So we can do algebra on functions. We can combine them using addition, subtraction, multiplication, and division by performing operations with the algebraic expressions that appear on the right side of the equation. The domain for each of these functions consists of all real numbers that are common to the domains of both the functions. So we use d sub f to represent the domain of f and d sub g to represent the domain of g. The domain for each function is the intersection between the two. In the case of a quotient function, we must remember not to divide by 0. So we add further restriction that g of x cannot be 0. So let f and g be two functions. The sum, f plus g, the difference, f minus g, the product, fg, and the quotient, f divided by g, are functions whose domains are the set of all real numbers common to the domains of f and g, defined as follows. So the sum, f plus g of x, is equal to f of x plus g of x. The difference, f minus g of x, is just f of x minus g of x. The product, fg of x, is f of x times g of x, and the quotient, f divided by g of x, is f of x divided by g of x, provided that g of x is not equal to 0. So let's use f of x equals 2x minus 1 and g of x, which is equal to x squared plus x minus 2, and we want to find each of the following functions and their domains. So f plus g of x. Well, that is just f of x plus g of x. But this is 2x minus 1 plus x squared plus x minus 2. So we just want to combine like terms. We've got 2x and x. And I've got negative 2 and negative 1. So we get x squared plus 3x minus 3. And so the domain of this is all real numbers. Or from negative infinity to infinity. Now let's do f minus g of x. Well, this is just f of x minus g of x, and that's 2x minus 1 minus x squared plus x minus 2. So we want to distribute the negative to all three pieces in the second equation. So we have 2x minus 1 minus x squared minus x plus 2. Now let's go ahead and combine like terms. I've got 2x and negative x. I have negative 1 and positive 2. And so we end up with negative x squared plus x plus 1. And so the domain of this one is again all real numbers. go ahead and try the third one. Fg of x. This is f of x times g of x. That's 2x minus 1 times x squared plus x minus 2. So now we just want to multiply. That's 2x cubed plus 2x squared minus 4x minus x squared minus x and plus 2. So now let's just combine like terms. I've got 2x squared and negative x squared. I have negative 4x and negative x. So we end up with 2x cubed plus x squared minus 5x plus 2. And so the domain again is all real numbers. So all of these have been all real numbers because it hasn't involved any even roots or any division. So go ahead and pause the video and try the last one for yourself. So f divided by g of x, that's f of x divided by g of x, but that's 2x minus 1 over x squared plus x minus 2. And that can't be simplified at all, so we're just going to leave it. Now the domain on this one will not be all real numbers because we have division involved and we can't divide by 0. So we need to set the denominator equal to 0 to see what can't be involved in the domain. So we have x squared plus x minus 2 equals 0. Well, this is just x plus 2 times x minus 1 equals 0. And setting each piece equal to 0, you get that x equals negative 2 and x equals 1. So my domain is everything except negative 2 and 1. So negative infinity to negative 2, union negative 2 to 1, union 1 to infinity. Let's go ahead and try example number 3. So let f of x be the square root of x plus 3 and g of x be the square root of x minus 2. We want to find the following. So we have f plus g of x. So this is just f of x plus g of x. But this is just the square root of x plus 3 plus the square root of x minus 2. Now we can't combine these because the square roots don't look exactly the same. Now the domain. So the first thing we need to do is we need to look at the domain of f of x and the domain of g of x because we have even roots on both of them. So the domain of f, remember whenever it's an even root, we set the inside piece greater than or equal to 0. So x plus 3 is greater than or equal to 0. But that just means that x is greater than or equal to negative 3. The domain of g, we do the same thing, but in this case, we have x minus 2 is greater than 0. which means that x is greater than or equal to 2. And so what we want to do is, let's go ahead and write these. This is bracket -3 to infinity, and this is bracket 2 to infinity. We want to find the intersection of these two pieces. And so let's just draw a quick number line just so we can see. We've got -3 and we have +2. At -3, it's greater than or equal to, and at -2, it's greater than or equal to. So looking at my line, where are both of my colors at? So both of my colors are from 2 up till infinity. So the domain of my intersection of f and g is just 2 to infinity. So let's talk about composite functions. So the composition of the function f with g is denoted by f of g, it's like a little circle, and is defined by the equation f of g of x. So all you're doing is you are plugging in one function into the other function. The domain of the composite function f of g is the set of all x such that x is in the domain of g and g of x is in the domain of f. So we have a two-part rule for the domain of a composite function. So let's go ahead and use the function f of x equals 3x minus 4 and g of x equals x squared minus 2x plus 6 and find f of g of x and g of f of x and g of f of 1. So I'm going to mark f of x in pink and I'm going to mark g of x in purple. So f of g of x, this is like f of g of x without the little circle. So I'm plugging g of x into f of x. So wherever I see an x, I'm going to plug in g. So we have 3x, but where x is, I'm now plugging in g. So x squared minus 2x plus 6 minus 4. Now we just want to distribute and then simplify. So we have 3x squared minus 6x plus 18 minus 4. And so what we have in common is a positive 18 and a negative 4. And so what I get is 3x squared minus 6x plus 14. Go ahead and pause the video and try the second one for yourself. So in this one, it's g of f of x. So I am plugging f of x into g. So wherever I see an x in the g function, I will plug in f of x. So this is, we've got x squared. So we've got 3x minus 4 squared minus 2 times 3x minus 4 plus 6. So let's go ahead and write this out twice so we can multiply and simplify. I've got 3x minus 4 times 3x minus 4 minus 6x plus 8 plus 6. So here we end up with 9x squared minus 12x minus 12x plus 16 minus 6x plus 8 and plus 6. So let's go ahead and combine like terms. I've got negative 12x, negative 12x, and negative 6x. I have 16, 8, and 6. So what I end up with is 9x squared minus 30x plus 30. And for g of f of 1, there's two ways of solving this one. So the first way is to use what we just found in b and plug in x equals 1 into the equation. So we start with 9x squared minus 30x plus 30. So we're plugging in x equals 1. So 9 times 1 squared minus 30 times 1 plus 30. But this is 9 minus 30 plus 30, which is just 9. Now let's just say we didn't figure out g of f of x first. So the best way to go about this is let's figure out f of 1 first. But this is just 3 times 1 minus 4. Or 3 minus 4, which is negative 1. So f of 1 is negative 1. We're plugging negative 1 into g. So g of negative 1. Well, that's negative 1 squared minus 2 times negative 1 plus 6. So we get 1 plus 2 plus 6, which is 9. So either way, you get the exact same answer. If you have not calculated out g of f of x, in my opinion, it's the easiest to go with the second route and simplify that way. So we need to be careful in determining the domain for a composite function because we had two parts to it. So the following values must be excluded from the input x. If x is not in the domain of g, then it may not be in the domain of f of g. Any x for which g of x is not in the domain of f must not be in the domain of f of g. So let's go ahead and try this with f of x equals 2 over x minus 1. And let's try it with g of x equals 3 over x. So let's do f of g of x first. So I'm plugging g of x into f of x. So wherever I see an x, I'm going to plug in g. So I have 2 over 3 over x minus 1. So we want to make this look a little prettier. We want to have one fraction total. We don't want to have another fraction inside. So let's go ahead and multiply by the LCD, which in this case is x. So we end up with 2x divided by 3 minus x. So now let's figure out the domain of this. So first, if x is not in the domain of g, it must not be in the domain of f of g. So let's look at g of x first. The only value of x we can't have is 0, and that's because we would be dividing by 0. So x cannot be 0, which means it can't be 0 in f of g. Now for any x for which g of x is not in the domain of f, it must not be in the domain of f of g. So now we want to look at our new defined function. F of g of x equals, we have that 2 over 3 over x minus 1. And so the only thing that's going to cause an issue is the denominator. So we have 3 over x minus 1 equals 0. So let's just add 1 to both sides. Then we get 3 over x equals 1. Or we get that 3 is equal to x. So we have two things that we can't have. We can't have 0 and we can't have 3. So the domain of my function, my composite function, is negative infinity to 0, union 0 to 3, union 3 to infinity. So you're looking at the back function first to see what x can't be, and then you're looking at the whole composite function to see what x can't be, and then you bring those two restrictions together. Now let's talk about decomposing functions. So when you form a composite function, you compose two functions to form a new function. It's also possible to reverse this process, and that is you can decompose a given function and express it as a composition of two functions. And there are numerous ways to do this. Try to make your life as easy as possible though. So express h of x as a composition of two functions. So we have h of x equals the cube root of x squared plus 1. You want that ugly piece that has any of the square roots, the cube roots, to just be one of our functions. So let's just say f of x equals the cube root of x. Our goal is h of x is equal to f of g of x. So I need to find what I'm plugging into the cube root of x, so they end up with the cube root of x squared plus 1. And so that means that g of x has to be x squared plus 1. And that would be one decomposition of my function. You can always double check your decomposition by composing your two functions. So f of g of x would then be the cube root of x squared plus 1, which is h of x. So that checks out.